in Vienna in the group of Andreas Nonnenkamp, and it's a pleasure to have you here, and I'm very looking forward to your talk. So please go ahead.
Thank you very much, Federico, for having me as the last speaker of the group seminar. And yes, so today what I'm going to present is our recent work on non-reciprocal many-body systems. And as you can see, like the title is a bit of a mouthful, and it's Interaction-Mediated Non-Reciprocal Dynamics from an exactly solvable model to generic behavior. And during this talk, I'll try to unpack all the different pieces that make up like this title. So I will try to start and discuss what do we mean actually with non-reciprocity in a quantum setting. Why do we need and which kind of exactly solvable model we want to present, and how this exactly solvable model is connected to more generic behavior. So can you see my pointer? Hope so. So with this,
yes.
we can start. Okay, perfect. This we can start, and we can start from discussing what do we mean actually by reciprocity. Reciprocity doesn't really have a specific notion, but in a nutshell, we can define a reciprocal relationship between two entities within a system, entity A and entity B, as the has the property that the effect that A exerts on B is equal to the effect that B exerts on A. As I said, there is not an all-encompassing notion of reciprocity in physics or in general in modeling, and maybe the first instance of a reciprocal relation that we found during our studies, like Newton's third law, which tells us that the force exerted from A to B is equal and opposite to the force exerted from B to A. And this reciprocity relation is strictly connected to conservation of linear momentum, for example, in a scattering event between two classical particles. And a question could be then, like, how can we break it? If we can violate this action-reaction principle from Newton's law, we can actually introduce non-reciprocity in the system. And one way to do it is through the mediation of a third medium. For example, if we have the two particles embedded in a medium which can mediate interactions between the two, then at this point, the particles can exchange momentum with the medium, and the effective forces that the two particles feel between each other can break and violate Newton's third law. Of course, this is because there is like a third party that can absorb linear momentum. Of course, this definition, though, it's quite restricted when there is a mechanical interpretation for our system, and it doesn't really give a natural extension to quantum system. But as I said, like reciprocity has encapsulates like a broad family of systems and notions, and another notion can be connected to detailed balance. So in a stochastic process, like detailed balance can be seen as another reciprocal relation. And it tells us that at the steady state, the probability of seeing a certain trajectory needs to be equal to the probability of seeing the opposite trajectory. And this is much nicer setup for thinking about reciprocity in quantum systems, since it feels much more natural and it's connected to stochastic processes. Of course, if we are at thermal equilibrium, then we know that detailed balance is always satisfied. And in this case, it comes from like this local notion of detailed balance. And so if we want to introduce non-reciprocity in a stochastic process or in a quantum system, what we want to think of is going out of thermal equilibrium. We want to violate it. And so we want to bring our system away from thermal equilibrium, where detailed balance is not respected, and we can have a net flow of probability in our system. So how can we do it? What's the first approach that we can have to think of like non-reciprocity in a quantum system? Well, if we want to introduce it in a quantum system, we can think of breaking hermithicity. And so, for example, in this case, we have a tight binding model. which is described at our Hamiltonian. But interestingly, we decide to pick different hopping rates between the two directions. So the the hopping, the transition of going to the right is different from the transition of going to the left. Of course, this is like the well-known Hatano-Nelson model, right? And we are dealing with a non-Hermitian Hamiltonian, which brings about different issues. The first one is that it's not really a fully consistent quantum derivation, right? Because then we don't have conservation of probabilities, our norm can decay, and in general we lose many of the nice properties that quantum system has. For example, like complete positivity and preservation of norm of trace. So is it possible to recreate a system that in this sense breaks reciprocity, so has like unbalanced hopping rates in a fully consistent way? And the first idea, of course, is like, well, we need, of course, as we discussed before, we need to go out of equilibrium. And the first way to do it is to couple our system to an external environment, which is not a thermal bath, right? And the description for a quantum system which is coupled to an external environment is can be generally described as like Lindblad master equation, where we have our density matrix, and the time evolution is controlled, of course, by the Hamiltonian part of our system. So the actual system Hamiltonian, and then the Lindblad jump operators, right, which describe the action of the environment on the system itself. And right, you can see this like retains. It's a completely positive and trace preserving map. So it's a fully consistent quantum mechanical description of our out of equilibrium system. If we want, right, to reproduce such an Hamiltonian or such a behavior, what we want is definitely to have a dissipator, right, like a jump operator, which acts on the bond, right? Because we want to introduce an asymmetry in the hopping, so an asymmetry in the relation between neighboring sites, how the two interact. And how can we do it? Well, this can be done by introducing these jump terms. So as we can see, we have recovered, like we start again from a fully Hermitian Hamiltonian, so where the hopping rates between neighboring sites are equivalent to the left and to the right. And then we introduce like this two-side loss term, which has like some interesting features. For example, the fact that there is a phase difference between the loss on site J and site J plus 1. And of course, to avoid having a trivial steady state, so if we don't want to completely deplete our system, we also introduce pump in the system, right? So we have uniform gain in this case, which acts equally on each side. So if one wants to have like an understanding why such a dissipator should actually should recreate our desired non-reciprocal dynamics, we can see it like by the fact that like this complex factor in front of the J plus 1 annihilation operator, right? When included in the Lindblad master equation that we had before, together with like the complex like the Hermitian conjugate of this jump, interferes with the hopping process, which is induced by the Hermitian part, so the coherent part of the evolution. And indeed, like such dissipator can actually be realized experimentally in like through cascaded quantum systems or via reservoir engineering. And if we look then at the dynamics, at the time evolution of observables of our system, for example, like the correlation matrix, one-time correlation matrix, we see that we can actually reduce the dynamics of the correlation matrix in terms of a dynamical matrix, which here is defined as like Hn, which is none other than like the single particle Hatano-Nelson Hamiltonian, right? So what we see is that we can recover the physics described in the Tano-Nelson model in a fully consistent way through a reservoir engineering or cascaded quantum system, using such, like, describing like the dissipation with such an operator. And the dynamics of our correlation matrix is described by a single particle Tano-Nelson Hamiltonian. Okay, so now that we're set, we want to understand, like, we have notion of non-reciprocity and also a recipe and ingredients that can actually introduce non-reciprocity in a quantum system. We want to understand how interaction can have an interplay with such non-reciprocity, and specifically if interaction can actually transfer, mediate, and redistribute non-reciprocity across sectors in our quantum system. So our starting point will be the Hatsugai-Komoto interactions that I'm going to describe, like, really soon. And we...
May I ask a question?
Yes.
On the previous slide.
Yes, sure.
So just a curiosity. So you said before that you need to introduce this gain, this LJ cube, to avoid to avoid a trivial steady state, right? Yeah. But also before you said that in the end, in order to observe this non-reciprocal dynamics, right, you are just looking at out of equilibrium dynamics. So
yeah,
is it really important that you have this trivial steady state? I mean, because it seems to me that looking at the Hamiltonian you just derived, that, right, this K does not influence the asymmetry between the hopping rates.
Yes, so it depends what you're interested in. Like, if you are just interested in, like, the dynamics of your system, so you want to see how, like, this, let's say, first dissipator here that we have affects the propagation of excitation in your system, and you start from, like, an initial state and you want to see how it relaxes, then you can actually avoid inserting, like, incoherent pump in your system. But in many cases, like, for example, if you want to discuss dissipative phases of matter, so you want to talk about the actual phases of your system, then those are defined usually with respect to the steady state. And so you, like, one of the desiderata would be to have a non-trivial steady state. So a steady state which is not just a vacuum, because then you can actually describe the different phases of such steady state. So, in a way, one can say, I want to study dynamics, and so I don't need pump, or I want to study the steady state, and so I would like to have pump in order to, do not deplete completely my system.
Okay.
Okay. Okay. So going back to what we were discussing, right? We now have, like, ingredients. We have non-reciprocity. We need interactions. And the system that we're going to consider here is, like, a one-dimensional lattice with spin 1/2 fermions. As you can see, again, we have our tight binding model. So we have our hopping rates. We have two possible spins, right? Spin up and spin down. And we have our two-side loss, which introduces non-reciprocal behavior. And again, we discussed just before, we have incoherent pump in order to be able to have, like, a non-trivial steady state in our case. And here are the interactions, which are known as Hatsugai-Komoto interactions, which appear quite frightening at the beginning. And what these are all-to-all correlated hopping that preserve the center of mass. In real space, that's, like, how they look. So basically, right, if one particle hops, like, if we have, like, one interaction event, one scattering event, and one particle hops to the right by 1, then the correlated particle needs to hop to the left by 1, and the same for any other direction. And why do we care? Why do we want to use such particles, such interactions? Why is it interesting? It's interesting when we transform our Hamiltonian, actually, our entire Liouvillean, in momentum space. So we assume that we have periodic boundary conditions, and then we transform it into K space. And this is how our model becomes, right? We have, right, the hopping part reduces to our dispersion relation that we have here. And then what's particularly nice is that these interactions in K-space become local in momentum. So we have density-density interactions within the same momentum mode. And this is the first nice structure for our Hamiltonian, but also, of course, like our gain, which was uniform in real space, is still going to be uniform in real space. And sorry, here there is a mistake. This should be a 1. Well, here, if you also want to transform our two-side loss, so our non-reciprocal losses in K-space, we see that we can have like the equivalent description is given in K-space with like a jump operator, which is local in K-space, so it acts individually on each K-mode, and with a dissipation rate, right? We have like now a gamma K sigma, which depends on the mode, right? And this is also a second way we can think of, like we can understand why such dissipator introduces no reciprocal propagation, right? It's because different K-modes experience different dissipative rates, and actually in the continuum limit, there is one mode, in this case pi half, which is completely dark, and it's not subject to any dissipation. So it actually seems quite trivial to, like at this point, the system, because the entire Liouvillean decouples into each K mode and can be written down as a direct sum of each Liouvillean for each K mode. And also, if one, like we notice that, right, both the non-interacting and interacting term only include densities, and so they commute between each other, and so we don't expect to have any correlation build up in the steady state, right? Like the correlation matrix in the steady state will decay to a diagonal matrix, since the interaction do not create any correlation between different K modes. And so the question could be like, are all steady state properties trivial, or can we do something, or are there other observables, other quantities that we can look at to see if we can have non-trivial dynamics induced by interaction and non-reciprocal dissipation. And so,
sorry, Pietro, can
yes.
I ask a question?
Yes.
I think I missed the story in a way. Why you introduced the interaction terms going like the U term?
Yeah,
I missed the motivation.
The motivation is that
against the general story.
Yeah, the general story, right? The story is we have no reciprocity, and we want to see what's the interplay between no reciprocity interactions, and if it's possible through interaction to redistribute or to transfer no reciprocity.
Okay.
Right. So we need an interaction term, and we take this specific interaction term because it's particularly nice algebraically, right? Because it decouples our system for each K mode. Right, and so we treat each K mode separately, right? That's why we like it. Yes. So then, like, if the static steady state properties are trivial, what about the dynamical properties of the state? And by dynamical properties of the state, I, for example, mean the propagation of single particle excitations, which is encapsulated by the Green's function, right? So what we want to study now are not like one-time or single-time correlators, but are two-time correlators. So the idea is like we have our steady state, we insert an excitation. In this case, we are focusing only on the spin-up sector. So we only put one excitation at time 0 on the spin-up sector, and then we remove it at time t, and we look at how what's the overlap between the two states during the evolution, right? This is the meaning of this function. This is actually the retarded Green's function. And specifically, since our steady state, like our system is translationally invariant, we can study the Green's function for each K mode, and then like through Fourier transform, we can just recover the Green's function in real space. And this quantity can actually be computed exactly via the quantum regression theorem, also for open systems. And specifically in our case, what we find is that the equation of motion closed. So this nice Hamiltonian that we had allows us to get an exact closure of the equation of motions. And indeed, we can compute the time evolution of our operator that we care for the retarded Green's function, and it only couples to a higher order term, which is this conditional operator on the occupation of the opposite spin sector. So again, we are looking at the time evolution, so at the propagation of excitations in the spin-up sector, and we see that the evolution of this operator is also dependent on a compound operator, which it takes into account the occupation of the spin down sector, so of this opposite spin channel. And the time evolution of such vector is controlled by dynamical matrix, and this is the form. It's a very simple dynamical matrix. It's a 2x2 dynamical matrix, which is non-Hermitian, right? As we had also before in the case of the correlation matrix that we showed had a single particle at an Lorenzo model. Of course, like such 2x2 matrix can actually be solved, and we can solve the find the eigenvalues exactly and have like an explicit expression, which tells us how the single particle excitation on the spin-up channel is affected by all the ingredients that we have in our system. And as we can see, right, like we have the imaginary part, which depends on the dispersion relation, of course, and on the interaction term. And then here we have a compound dissipative part, which depends on the direct dissipation and pump that we have on the spin-up sector, plus a contribution from the spin-down sector. And what?
Sorry, Pietro. This capital gamma K, where the small gamma K in the previous slides
are the sum of the pump and the the dissipation. So it's the total fluctuations experienced by the system. Yes, thank you for coming along.
Okay.
Yeah, thank you. So, right, and these are. Right, like what we're saying is that like the time evolution is controlled simply by the eigenvalues of the dynamical matrix, where we have the coherence evolution and a dissipative contribution here. And we can see that, of course, like if the interaction is 0 and or the pump is 0, then the eigenvalue will just be given by the diagonal elements of the matrix, since the matrix will become triangular. And this is not particularly remarkable, right? Of course, if the interaction is 0, then the propagation of the excitation on the upspin will only be affected by what happens on the upspin. But if our interaction is finite, and also if our pump is finite on the spin down channel, and we go back, so that this, in a way, we recover what we were saying before, that we want to have a non-trivial steady state, right? Because what we can think of now, we have basically a sea of driven dissipative matter in the spin down sector, which we have created through like this non-reciprocal dissipation and pump. And we insert a spin-up excitations on top of it, and we want to look how the propagation of such excitation is renormalized by the presence of the spin-down driven dissipative path. And we can see here that whenever the interactions are finite, and also the pump on the spin-down sector is finite, then we get a hybridization from the coherent channel and the dissipative channel. And in particular, the interaction strength mixes with the dissipative terms on the spin-down sector, which is the opposite sector respect to what we are caring for the propagation of the excitations. Okay, and so like the question was, right, how are the spin-up then, like how are the spin-up excitations affected by the dissipation on the opposite spin sector? And here we have again, I just like put again like here our dynamical matrix and the eigenvalue. And of course, like if the interaction is 0, then the propagation will just be the usual ballistic propagation, since the spin-up sector, right, will not feel any dissipation coming from the spin-down sector. and everything will be just a trivial coherent propagation. If instead we consider like an intermediate case, so we consider having not like the non-reciprocal loss, but a uniform loss, then of course like the presence of a driven dissipative channel beneath it, which interacts, it's gonna dephase our excitations on the spin-up channel reciprocally. But interestingly, instead, if like in the case that we care about, so when this gamma k depends on k, right, on each momentum mode, then each momentum mode will experience a different dephasing. And even if like our spin-up channel doesn't have any direct coupling with the bath, with the reservoir, through the interaction, we can mediate non-reciprocity. And this is the case of finite interactions. And what we can see is that our excitation acquires a non-reciprocal dynamical feature despite the fact that it was not directly coupled to the reservoir. So basically, we show that the Hatsugai-Komoto interactions can mediate non-reciprocity across different sectors. And here in this little inset, you can see that as like here we have in the x-axis, we have the center of mass of our excitation. And we can see that as U is tuned and increased, then like the center of mass in its time evolution becomes like more and more directional. Okay. Now,
may I ask a question?
Sure.
I don't know what happened. One moment. You okay now? Maybe now I can I can talk. So no, I have a doubt. Like in this case, okay, before you said that you had non-reciprocity because of this particular structure of the jump operators. Now you're saying that you have non-reciprocity because of this structure of the interaction, this non-zero U. So in this system, so in the case you are considering now, what is the source of this reciprocity? Is it one? Is it the other? Is it both?
So it's both, in the sense that we have the spin down sector. So right, like so let me go back. Right here we are computing the spin, we want to look at how spin-up particle excitations propagate in our system. But we only have dissipation on the spin-down sector, basically. In this picture, in these plots here, like dissipation is only present directly on the spin-down sector. So without interactions, the spin-up particle cannot see any source of dissipation, of course, because like they are not coupled in any way to the spin down sectors. So this is U equals 0, right? And there is no possible source of non-reciprocity.
So basically you are saying that okay, you are putting dissipation only on the spin down sector, so you would have like a non-reciprocal dynamics in the spin down sector while a fully reciprocal in the spin up sector, right? And now we are coupling both.
Yes,
with
exactly.
This interaction. Okay.
Yes, and the interaction couple them both. And what happens is that after we couple through the interactions, the spin-up sector, which initially didn't have, was completely closed, right? It's particle conserving, doesn't have any coupling to the reservoir, the spin-up sector. But after you couple it through the interactions, which are density interactions in this case, of an artificial or fine-tuned nature, if you want, but they are density interaction, then also the spin-up sector acquires these non-reciprocal dynamics.
Okay.
Okay.
So you are coupling basically, just final remark. So you are coupling in the end the top spin sector to the reservoir via the spin down sector in the end, no?
Yes, exactly. Exactly. Yes, right. And this is basically encapsulated in this part of the eigenvalues, right? Whenever U is finite, right? Both eigenvalues, so the dynamics of also the spin-up excitations, will acquire a dissipative character through the presence of the bath in of the reservoir in the spin-down sector.
And the dynamics is fully Markovian, right? Because
yes, it's in blood. Yeah.
Okay. Thanks.
Yeah, no worries. All right. Okay, so far we have looked at the system in real space, but also to be able to compare it, right? Because so far what we've studied is a quite fine-tuned interaction, and so we would like to see if such phenomenology is present for more generic systems, how it compares, and the object through which one can do so is the spectral function, right? So what we look at now is the momentum result spectral function, which is just the retarded Green's function, but we compute it in k-space, so we resolve k-space, and also in frequency space, right? And in general, like such function gives us access to the band structure of the system, the energy level of a many-body system, right? In our case, but also in general, we can always write it down in such a compact form, right? Where here we can see, right, that we have an energy, we have our frequencies. This is like the dispersion relation, so it's the the energy contributions coming from the non-interacting system, and this is the self-energy, right? Like this term here encapsulates all the interaction effects that renormalize, so they change and modify the propagation of an excitations, which is dressed by the presence of the many-body state around it. And of course, for our Hatsugei-Komoto model, we can compute it exactly, right? This is the self-energy for the Hatsugei-Komoto model. So what we see here is that we have an energy shift, which is due to the occupation of the opposite spin sector and depends on U. And here we have higher order terms, which combine all the possible scattering processes within each K mode that lead to the renormalization of the propagation of our excitations, right? And we see that here, in this part here, since we are considering only dissipation on the spin down sector, we have the total fluctuations that enter in the broadening of our spectral function, right? And we can have a look at different situations and how our spectral function looks like. And so here in the first case, and these are our spectral function for three different scenarios. Like the first scenarios is simply uniform loss and uniform pump in our spin down sector. And there is no asymmetric feature, right? Like we have two bands, two dispersive bands, right? One comes from the unoccupied dispersion relation. So we have like our epsilon k, and in the other case, right, we have a shift given by this hearted term here. So if our spin-up excitation occupies a K mode, which is already occupied by a spin-down particle, then it's going to populate this upper branch. But this is completely reciprocal. And so a question is like, how does this change when we add non-reciprocity? And when we add non-reciprocity, it becomes strongly asymmetric. And we can get an intuition of what's happening in, for example, in this case where we have no reciprocal loss, so in the central plot, and we still have like two branches. So we still have the two branches that characterize our Hatsugei-Komoto model, but they are heavily asymmetric. This can be understood because, right, the dissipation acts differently for different K modes. And for example, in our case, pi half is a dark state. So it's not affected by dissipation, and only sees the uniform gain. Such uniform gain heavily populates the spin down mode, and it suppresses fluctuations. And so whenever an excitation in the spin up channel is introduced as such K mode, it's going to populate the upper branch of our initial system, and it's going to do so with a high lifetime, with a very high lifetime. Instead, away from such protected point, the dissipation acts and enhances the fluctuation in our system, and so the branches in our spectral function broadens. Of course, as we increase the interaction, then the hybridization between the incoherent contribution and coherent contribution becomes stronger and stronger. And at some point, we lose this nice two-branch picture, and the two-branch hybridize completely. But what is preserved is like this high lifetime and very narrow bandwidth of excitation at pi half. And this is due to the fact, right, that basically at pi half, the momentum, that momentum mode does not experience dissipation. Okay, so this is like the object that we're gonna carry over to try and see what happens away from the fine-tuned case, so away from the Hatsugaiko motor mode. And to do so, to move towards more generic behavior, we still consider a spin 1/2 system in 1D, but now with Fermi-Hubbard interactions, right? So Fermi-Hubbard interaction in real space are density-density interactions, which are now local in real space. So particles only interact and scatter when they occupy the same mode, the same site, the same real space site. And in momentum space, what does it mean? It means that we have scattering to all possible and available momentum modes as long as total momentum is conserved, right? So this is exactly this same interaction term, but in momentum space. And again, what we have is our non-reciprocal loss, right? So we have a k-dependent loss here acting only on the spin-down sector, and here we have our uniform pump acting on the spin-down sector again. So we are in a very analogous situation to what we had before. We have a driven dissipative spin-down sector, which is populated through this uniform gain and depleted through this non-reciprocal loss. And what we change now is the interaction term. So the only ingredient that is now changing is the interaction, which is not relegated to be only to scatter particle in the same K mode, but it can scatter particles across different momentum modes. Of course, we lose exact solvability. We cannot do things completely exactly analytically, but what we can do, we can still compute the Green's function perturbatively. So we can start from the limiting case of small interactions and try to compute a higher order term as we go along and see how this compares to the Green's function that we found for the Hatsugaiko motor model. And of course, here we have a spin 1/2 Fermi-Hubbard model. So at first order, right, the interaction acts as a uniform potential, which does not carry any spatial information, any momentum information. So that can be neglected from our Green's function because it doesn't carry any non-reciprocity information whatsoever. But what we can do is that we can study at second order the Green's function. So a second order in U. Here we start having some interesting and non-trivial momentum exchanges, right? We can think of having our nice excitations, which is introduced at momentum K in the spin-up sector. And through an interaction event, it scatters off the spin-down sector and it creates a particle Hall excitations, right? So what happens is that it's creating a particle, which momentum is P minus Q, and a Hall excitations and momentum P. And it propagates throughout the system in the presence of these two excitations, right? And these two excitations are embedded in this driven dissipative environment, and they carry information about the reservoir that is coupled to the spin-down sector. And this is the self-energy that indeed we can compute at second order for the Fermi-Hubbard interactions, right? And we see that indeed what we have a scattering event across all momenta, so possible combination of momenta P and Q for our particle Hall excitation. We have our phase space vector, because if we want to excite a particle Hall excitation, well, we need to have a particle in momentum P, and we have to we need to have space for a hole in momentum P minus Q. And then below we see that here we have our the energy of our excitations, right? We have the particle, which is now propagating in the spin-up sector with momentum k plus q. We have our hole at momentum p, and we have our particle excitation at momentum p minus q. But what's interesting is now, right, as we said, like the spin down sector is driven dissipative because the spin down sector is directly coupled to the reservoir. And so the particle and hole excitation carry fluctuations coming from the reservoir, okay? And this is indeed like encapsulated by this term here, this finite bandwidth of our excitations in our self-energy. And indeed, if you look down now at the plots of the spectral function and the Green's function for the Fermi-Hubbard excitations, what we see is that also in this case, our system, our spin-up excitation propagates non-reciprocally, and we recover the features that we had also for the Hatsugai-Komoto model. So we have a directional propagation of the excitation, which is also accompanied by the fact that we have a narrow line width for excitation at a certain momenta, in this case, and a broadened line width at the opposite momenta. So we now have different pictures. We have established that non-reciprocity can be transmitted between different sectors with Hatsugai-Komoto interactions, and we had a certain understanding and intuition for that. Now we also have a description for the transfer of non-reciprocity with like Hubbard interactions, so local interactions, which are much more natural. And the question remains, like, how are the two connected? Like, is there a way to understand or to connect these two pictures? And we can, again, like compare the Hatsugai-Komoto and Fermi-Hubbard self-energy. This is right, like the Fermi-Hubbard self-energy that we just had like in the previous slide. And then we also previously computed the Hatsugai-Komoto self-energy, but that Hatsugai-Komoto self-energy was computed at all orders in U. It was exact. And so what we can do for comparison is to expand it at second order in the interaction strength. And what we can see here is that the Hatsugai-Komoto interaction actually reduces to the same functional form of the Fermi-Hubbard interaction, where the scattering phase space, so where like the scattering is only allowed within the same K-mode as it is like the feature of the Hatsugai-Komoto model, right? In the Hatsugai-Komoto interactions, the interaction term was forced and acting within each K-mode independently. And as we can see here, right, at second order, so here we have the second order for the Fermi-Hubbard interactions, and here we have the second order for the Hatsugai-Komoto interaction. Again, we have this phase space picture for particle and hole availability. Then we have our energy contributions from the particle hole, which, since they are bound to stay in the same K-mode, they cancel out. And so we just have one contribution, epsilon k. And again, like since we're projecting everything on the same K mode, here we have like the sum of the fluctuations on P, on momentum P, and on momentum P minus Q. And here instead, like everything is projected onto K. And so we only have one contribution of fluctuations coming from mode K, right? And what you can see here, again, like analyzing spectral function, we still have like this nice feature. This is like the Hatsugai-Komoto model, where like we have final line width at a certain momentum. And here again, like for the Fermi-Hubbard model, we again see that the excitations of a certain momenta are longer lived compared to the asymmetric ones. So to summarize and conclude,
sorry, Pietro, but yeah. Why do you want to compare them in the first place? I think I missed this point.
It's just to see if there is a common picture for what we learn from the Hatsugai-Komoto model, right? Like, so we have an exactly solvable model, which is quite fine-tuned. So it has like some interactions which in real space are all-to-all and very engineered. But it shows a certain phenomenology. namely the phenomenology is right. We can mediate interactions. We can mediate non-reciprocity through interactions, and we have a certain understanding of why that's the case, like why it's the case. If we take like a more general system, of course, we lose integrability. We still show the same phenomenology, but like a question that might arise is: are the two connected? Like, is the same phenomenology is this like common phenomenology has like a common understanding, a common microscopic mechanism, or can we draw a connection between the two, right? Because it could be that like maybe they say they show similar behavior, but they are like since they appear to be so far apart, right? Like in one we have all-to-all interaction, in the other one we have very local interactions. Is there any chance that we can make sense of the two and compare the two? And like the answer is yes, in this specific way, right? In the sense that the Atsugai-Komoto self-energy is actually equivalent. It's analogous to the Fermi-Hubbard self-energy when you force your particle Hall excitations to scatter only within the same K-mode. So you don't allow scattering across the entire momentum space, but only within each momentum mode, right? So also like for the question could be, okay, what if instead of having just like scattering across either all momentum modes or only one momentum mode, we interpolate between the two. So like, I think like this connection can open up like some questions that could like allow to interpolate between the two cases, right? So this is why we wanted to compare the two to see where do they stand? Do they stand in completely different categories of a space of interacting systems, or can they be connected? Are they just like two opposite sides of a spectrum, right? Mm-hmm. Does it answer the question?
Yeah.
Okay. Yes. Great. Yes. So, right. Just like in conclusion, final remarks. We like in this presentation, what we saw is that we have a notion of non-reciprocity in a quantum setting, and this notion is quite specific in this case and regards the propagation of excitations across the system. We introduced an exactly solvable model which shows non-trivial interplay between non-reciprocity and interaction, and it's the Hatsugai-Komoto model. And the main feature that we addressed here was like the mediation of non-reciprocal dynamics through the interaction term. And we also compare it with we also show that this phenomenology survives in more general scenarios, for example, in case of Hubbard model, and that we can recover the Atsugai-Komoto model starting from the Fermi-Hubbard model as the limiting case where particle Hall excitations are projected into the same K-mode. So with this, I finished, and thank you very much for your attention.
I don't know how to clap in Jitsi. Okay. Thanks, Pietro. I have one question. Maybe it's a bit general, but so I am sure you know that all this reservoir engineering to have the Atano-Nelson model was developed mostly for bosonic systems. Yeah. And also in the framework of topological amplification. So I was wondering, does it make sense to do a similar studies like the one you did for bosonic systems? And is there like a bosonic version of this Atsugai-Komoto model?
Yes. So indeed, right. Yes, one could have of course, it's very general. In the end, one can think of polarized bosons. Right here, instead of having fermionic operator, you just have bosonic operators, and you have two different families, right? Two different flavors of bosons, and you can look at what happens in that case. What one needs to be careful is that for bosons, the equation of motion do not close, right? Because here, if I compute the equation of motion for CK, right, I will compute them, right, in my Hamiltonian, it will couple to this higher order term, right? Because I have interactions, and so it will, through the commutators, it will couple to the equation of motion of this term here. What's nice for fermions is that even if when I compute the equation of motion for this term, right, and I get to the interaction term again, then I will have an additional nk factor, right, because I'm computing again the evolution through the interactions. For fermions, right, nk squared is nk because of the statistical fermions. For boson, instead, you would couple to a higher order term, and you would lead to an infinite hierarchy. However, like, there are ways that one can exploit certain symmetries, even in the bosonic case, since we still have a full decoupling of all modes, to solve exactly the Liouvillean, but it's a bit more involved, and you need to go away from this simple equation of motion picture. But yes, one can be able to do so also for bosonic systems. So yeah, it's possible. Yeah, and you can do it like exactly. You can do it exactly. It's just more involved, a bit more involved.
Any other questions?
Yeah, I have a question. Can you go one slide back?
Yes, here.
Or one more to where you introduced this, or where you show. So no, maybe it's in front. Sorry, where you show the propagation of this excitation with the long range potential. Yeah, exactly there.
This one.
Yeah.
Oh,
so if I understood.
Oh, yeah. Sorry.
Yeah, no problem.
Okay.
Yeah, so it's more of a curiosity, but so on the left you have no interaction, and on the right you have a long-range interaction turned on. But so I would expect this propagation to sort of break this light cone that we see here, right? Because we give some long-range hopping, but or some long-range term. But this doesn't seem to be the case from the image. Is this from the nature of the interaction, or is there a way to understand this?
So in this case, like, you can understand it because right, it's long range, but it has like a very specific structure. And I like to think about like this interaction more like in reciprocal space, so in momentum space, than in real space. And in momentum space, like, each mode is affected, like each spin-up excitation at each mode k is affected only by what happens at the same mode in the spin-down sector. And so in a way, you still have like a continuous, right, like here, my point, right, like you still have like this nice continuous like hybridization of coherent and incoherent contributions, right, which have like this very smooth functional form, right? So each mode is then, when you Fourier transform, each mode will still retain like some smooth features, so you will not have like this huge disruption that you talk about. But if you, for example, like here I don't have it, but because here I only discussed about excitation, like propagation of the excitation. So we have the steady state and we put an excitation on top, but you can also study the evolution of densities, right? So you have like an initial state and you want to look how does this initial state evolve in time, right? So you look at the density, not at Green's function, and the density contain much more structure. Also like the incoherent, in the sense like incoherent, so out of phase structure. And for the density, you see what you're talking about. Like, you see that like there is like a cone, like a light cone, which propagates reciprocally, but in the background you also have the formation of a finite density background, indeed, which is due to the fact that like these interactions are quite non-reciprocal. But you still have like the survival of such a light cone. Right. So in a way, like your intuition is correct, right? Like, if you look at the density, there is a uniform background on top of which you have like an enhanced propagation of particles in one direction.
Okay, I see. So to break, why here we don't have this breaking of Lieb Robinson type bound is because we are doing it in the steady state and looking at these at the excitations from the steady state, right?
Yeah.
Okay. Thank you.
No worries.
Okay.
Can I ask a very brief question before we finish?
Yes.
So it's a bit of a question on the outlook of this guy. I don't know what you plan to do with this kind of system, but for instance, it seems to me that in this work, right, you consider the propagation of an excitation right on top of an uncorrelated steady state, right?
Yes.
At least in the So you plan to do some study?
Yeah.
Okay.
Yeah.
So
like
what would you expect to change? I don't know if you have some intuition already.
One thing that I'm interested in is exactly like here. I think for example, right, what if right here we discuss non-reciprocity mainly as like a directional propagation of excitations, right? But can we have in a quantum setting like non-reciprocity as like a breaking or a violation of action-reaction principle, right? And so you can think of having like one idea could be you have like your bath, you have like let's say a sector of your system which is out of equilibrium, and it's brought out of equilibrium through this like non-reciprocal dissipation, right? So it like has a certain current, and it breaks like inversion symmetry. And then on top of it, like, so you have like this non-reciprocal chain basically. And then on top of it, you couple it to another chain, which is completely at equilibrium. And you do it in such a way that when you integrate out the bath, like the chain which is underneath, so the out of equilibrium bath, this chain like mediates interactions between the particles that stay on top, right? So if you have more particles and you integrate out the non-reciprocal part, then what you see is that these particles actually interact between each other, but they do so in a way that violates this symmetry. So you basically have like an interaction kernel, you can see, which is retarded in time and asymmetric in k-space. And so the question is, does it lead like to some of these very fascinating phases, many body phases that one sees like in classical systems? For example, pattern formation, like traveling charge density waves or like limit cycles. So that could be a way, right? So you have your spin down bath, if you want, and you integrate it out. Of course, in this case, you cannot do it. You cannot do it because it's quadratic. Like here, it's, let's say, like in the Fermi-Hubbard model, you cannot do it nicely because it's quadratic, right? It doesn't enter linearly, so you cannot integrate it out exactly. But if you think of like a more, I don't know, ingenious coupling, then would like the particle in the spin-up sector feel non-reciprocal interactions between each other, right? That this could be like an outlook, right, for this. It's something that I'm working on at the moment.
Okay, thanks.
Yeah.
Okay. Yeah. So thanks, Pietro, for a very nice talk. Very, very interesting work.
Thank you.
So I guess I will maybe see you around in conferences, and
yeah,
have a nice summer.
Yeah. Enjoy summer too, and thank you for having me. Bye. It was a pleasure. Bye bye.
Thanks a lot. Thanks a lot. Goodbye. Goodbye.
Bye.
Ciao. Thanks for the talk.